That line's not moving.
Okay then. So what did we do last time? Last time we were focusing on linear congruences. And I know the visualizer wasn't functioning last time, so I'm going to do a few examples on the board today of this before we move on to the next topic. I've requested them to fix it, so I'm going to go over there and check it today, make sure it's been fixed and ready for tomorrow. So what we were doing last time, we were studying linear congruences, which are problems of the form, this form here, ax congruent to b modulo n. And this is our simplest case of the general problem of solving polynomial congruences. So we got to start with the simplest case and understand that well, and we'll go to tackle more general cases. So we have 3 separate results, I think, on this. First one dealing with, our natural intuition, when you see ax equals b, your natural intuition is to think of x. Of course, in this context, we don't say dividing by a, we say multiplying by the inverse of a. But we know modulo n, inverses don't always exist. Only certain congruence classes modulo n have inverses. The ones that do are the ones that are co-prime to n. So if the GCD of a and n is 1, that means yes, it's the nicest situation. The inverse of a exists. So you multiply both sides by the inverse of a, you're left with x on the left-hand side, and a inverse, although it's presented slightly differently there it's presented as a to the power of the Euler totient function minus 1. But that's just one way of expressing the inverse of a. So this is x equals a inverse times b. And that's your solution, okay? Because this is just one congruence class over here. Remember, the inverse of a congruence class, if it exists, it is unique. It's just one single other congruence class. Just as in other situations, inverses are always unique. You know, the inverse of a matrix, it's just one particular matrix. There aren't a few different inverses of certain matrices. Similar situation here. Inverses are unique. So that's your one and only one solution. That's the kind of simplest case. But then we have to think about, well, what if the thing isn't co-prime? What if the GCD is not 1? So we proved a second result. Here's a general GCD. The GCD of a and n being equal to d. Okay, there's no restriction on d there. It's not said d is equal to 1. D could be anything. And this tells us when, gives us the conditions for when solutions exist and when they do not. It says the solutions exist if and only if this greatest common divisor divides that other constant term in the linear congruence. If and only if d divides b. Okay, we worked through the proof of that last time, so won't work through it again. Okay, so now we know there are solutions when d divides b, otherwise there aren't. The last result tells you exactly what the solutions are and how many of them there are, and gives you like a complete specification. So this last result is when the GCD of a and n, coefficient of x, and the modulus of d, and d does divide b, so there are solutions by the previous result. Then it says there's exactly d solutions modulo n. These are representatives for them. T plus I times n over d. N over d is this fixed quantity. I is this parameter here, which is going to the integer 0 through d minus 1. So there's d values of I. And what's the t? The t is the single unique, is the representative of the unique solution modulo n over d. Remember, n over d is an integer, because d is a divisor of n. D is the solution of the reduced congruence. When you divide all 3 parts of the congruence across by that number d, and that gives you a congruence that is covered by the first result. Because after you divide by the greatest common divisor of a and n, after you divide them both by that greatest common divisor, the bit that's left behind, the a over d and the n over d, they will be co-prime. So that is covered, that last congruence is covered by the first result. This quantity a over d will have an inverse modulo n over d, so you multiply both sides by that inverse, there is a unique solution to this congruence, and t is a representative of that. So you choose your t, by convention you always choose the smallest positive one, it's the easiest one to handle, to work with. bring it up here, then you've got the parameter I and this fixed value n over d, and that will generate representatives of the d different solutions to your congruence. I didn't have the board available last time, so I will go through an example or two now. But any questions before we do that? Any questions about the statements of the results, or indeed any steps in the proof that we worked through last time? Okay. So let's choose an example. Switch to the overhead. So there's two examples there. There's an exercise of 6.1. So let's go for a few of these. Any particular one you want to choose? Let's try 6 and 7. Hopefully I'll alight on one that does have solutions and one that doesn't. So let's look at question 6. So this is exercise 6.1. Question 6 is 36x congruent to 8 modulo 102. Does it have solutions? No, it's not immediately obvious. Doesn't leap off the page at you whether or not it has solutions. So you start to apply the results. Okay, so we don't know whether it has solutions, so we need to investigate. We need to work out the GCD of the coefficient of x and the modulus. Okay, you could go into Euclid's algorithm, or you could instead jump to prime factorizations because the numbers are fairly small. 102 is 2 times 51, so that's nice. 51 is a prime number. So we can see there GCD by looking at the overlap in the prime factorizations. Okay. What's the overlap in the prime factorizations? It's 2. Just 2. So the GCD is 2. So that's our D from the results. D. And
51 can be divided by 3.
oh, sure. Sorry. Thank you. So I was assuming 51. So that's called the growth in D prime.
Yeah.
When you think, when you confidently say something like,
we've got a specific number as prime.
yeah. Whenever you confidently claim a lowish number as being prime, then you find out it's not. So what is 3 times 17? So you say, okay, so I was wrong there. The GCD is 6. So watch out for growth in D prime. 6. So are there solutions? Do there exist solutions to this complex? We should know that now that we're looking at the GCD. Yeah. No. Why not? 6 doesn't divide 8, yeah. So that's what the second result said. It said there's only solutions if this GCD divides the constant. Yeah. 6 does not divide 8. So no solutions exist. No solutions exist by, let's just reference it by number. What was it? 6.2. Okay. So that shows you the power of the results, you know? I mean, it's not claim, it's just obvious that there's no solutions to that. Okay, so let's try and find one that does have solutions. So the next one has solutions. Probably. Yeah. 2 times 17. Yeah, I think that's solutions. Let's look at the next one. 34x congruent to 60 modulo 98. So again, we just need the GCD. So let's do it using prime factorizations again. So the numbers are very small. 98, what's that? 2 times 49. 49 is 7 by 7. Yeah, I'm pretty sure 17 is prime. Okay, so you can see the GCD there is, of course, 2. Yeah. 2 is the overlap of the prime factorizations. You could use Euclid's algorithm for sure. You would get the same result. So GCD is 2, and 2 does divide 6. So there are solutions to be found. Okay, so we've got a very good criteria for the existence of solutions, whether that GCD divides the constant term. So again, that's by theorem 6.2. And then we go into use theorem 6.3. That tells you, specifies completely what the solutions will be. So we're looking for a number. How many solutions? Expect 2 solutions, okay? Because the number of solutions is the same as that of GCD, meaning 2 congruence classes modulo 98 that you can put in here for x that we solved. Okay, there'll be an infinite amount of integer solutions, infinite amount of different integers you can put in, but they all come from just 2 congruence classes modulo 98. And so the way to find them is we consider the reduced congruence. Divided congruence, where you divide across by this GCD. So then we're considering 17x is congruent to 30 modulo 49. Now we need the inverse of we want to talk about we want to get the unique solution. So we need 17 inverse modulo 49. And I think I can do that in my head. See 2 approaches here. You can either run the Euclidean algorithm on 49 and 17. They're co-primes. You're going to get the value of 1. And then you generate the linear combination of 17 and 49 that's congruent to, that's equal to 1. And whatever the coefficient of the 17 is, that's a representative of its inverse, modulo 49. Or you can use the formula from Euler's theorem, where you, maybe that's what I'm going to use here. We'll use the calculator. We use the Euler-Toshin function value on 49, and you raise 17 to the power of 1 less than that, and find out what it is modulo 49. Yes, question.
Why did we get the 17 and 30?
Dividing across by 2. So we're reducing everything by 2, dividing across by the GCD. Yeah. So let's use Euler's. Was it Euler's theorem? I think so. Euler's result. 17 inverse is congruent to 17 to the power of 549 minus 1. Modulo 49. So that's equal to, now what is 549? 49 is 7 squared. So remember the rule from the product formula for working out the Euler-Toshin value. You use the prime factorization of the argument, so 7 squared, reduce the power by 1, it's 7, you multiply by 1 less than that prime, 6. 7 times 6. So it's 42. So that's 42 minus 1, so it's 41. Modulo 49. I'm not going to do that in my head. Sorry, guys. Can you do that in the calculator faster than me? I'm not sure you could. Is 17 to the power of 41, will that fit in the calculator?
It's power. It has 50 zeros.
Sorry?
It has 50 zeros. I'm assuming the calculator works it out but rounds it. So
Yeah. So you can't be
you're
sure.
gonna have to use the other method.
Yeah. So 17 to the power of 41. To the power of 41. So we'll have a look at that. Big. Big as that. Yeah, so there's. It doesn't end. Of course, it could only end with a load of zeros if it had 2s and 5s. It doesn't have 2s and 5s and 17. So the small will be the big modulo 49. There's a shortcut in Sage to do modulo just using percent sign. So it's 26. Okay. So the inverse is 26. There is an inbuilt Sage command just where you can ask for the inverse modulo. So just inverse modulo 17, 49, etc. So that gives us 26. So that implies that the solution here, 17x is congruent to 30 mod 49, if and only if x is congruent to 26 times 30 modulo 49. Okay, so for the last time, let's do 26 by 30 modulo 49, 45. $45, on 49. So that's -4. So that might have been easier to see if we've been looking for it. Okay, so that's our t that we're going to feed in the language of the results. So the solutions to the original congruence, 36x congruent to, 34x, wrong one, congruent to 60 mod 98, are x congruent to, so it's this solution plus I times n over d. Now the I started at 0, so the first solution will be that same 45. The next solution will be 45 plus 1 times n over d. So the n over d is that 98 divided by d and d to 2. So that's plus 49. So that's 45, or what's that? 94. So those are the two congruence classes, modulo 98, which solve the original thing. 34x congruent to 60 modulo 98. Okay, we should probably just double check that using Sage. There's a nice Sage command, which I think is solve something, solve mod. It's a solve mod command. 36 times x. X is always a symbolic variable that's available. And the thing, 34x is equal to 60. You have to tell it what the modulus is, 98. Sorry, it's 34. 34x. Cute. 94 and 45. Okay, so we're okay. Okay. So is that okay? So that's good. We've seen one with no solutions and then one with solutions. Any questions about it? Sure. Okay. It's quite a nice, straightforward process in the end. Okay, so now we're going to come on to the next section, section 6.2, or the final section in this chapter. It's not that long a chapter. And this is the Chinese remainder theorem. Okay, so it's quite a well-known result in number theory. And I guess it gets that name, Chinese remainder theorem, because there's a very famous example. You know, you can find examples of this type of problem posed in some very early Chinese writings. So apparently they have it from about the 1st century AD. You can find mathematical writings that are talking about these sorts of problems. Okay? So find a number which leaves the remainder 2, 3, and 2 when divided by 3, 5, and 7 respectively. Okay. So quote from Sun Tzu roughly translates into English. And we found in other early writings as well. If you look in the problems, there's a problem of Brahmagupta from India, writing in about the 7th century AD. So, I mean, they looked like these little curious problems, but you can tell that they were interested in, you know, okay, they're not really interested in eggs and baskets, they're interested in the properties of the numbers and what's going on. So here, you have a problem, you've got a basket of eggs, you've got some quantity, and if they're removed 2 at a time, you'll be left at the end with 1 egg in the basket. If they're removed 3 at a time, you'll be left at the end with 2 eggs in the basket. If you remove the eggs 4 at a time, you'll be left with 3. Remove them 5 at a time, you'll be left with 4. If you remove them 6 at a time, you'll be left with 5. But if you remove the eggs 7 at a time, no eggs at the end of the basket. So it's not hard to appreciate that those statements are really statements of that we would call them now, those are statements about congruence classes modulo various numbers. So if you're taking eggs out of this basket 3 at a time, really you're trying to do an integer division by 3 of the number of eggs in the basket, taking them out 3 at a time, and however many are left at the end of the process, either 0, 1, or 2, that's the congruence class of the original number of eggs modulo 3. So these are quite not, you know, although we've got our modern terminology and notation for it, but these are quite natural kinds of questions to encounter when you're investigating the mathematics of the integers, so which humans have been doing for a long time. Okay? So let's look at we'll look at the statement of the Chinese remainder theorem, and then yeah, we've probably got time to look at the proof of it as well. So the Chinese remainder theorem is a tool which you can use to solve problems like these. You use it to solve problems where you're faced with a number of kind of simultaneous equations, if you like, to using different moduli. Specifically, what we're going to assume is that we've got a set of moduli, M1, M2, all the way up to MK. Now, they aren't any old moduli, they are pairwise co-prime. So pairwise co-prime means if you take any 2 of them, they'll be co-prime to one another. Okay? So these k different moduli are completely different to one another with regard to divisibility. Okay? So they're not only are there no common factors shared in common between them all, but if you just select any pair out of them, there will never be a common factor apart from 1 between that pair of moduli. Okay? So they're completely kind of different moduli. Then if you're looking at one congruence class with respect to each modulus, what the Chinese remainder theorem says, so B1 modulo M1, B2 modulo M2, etc., BK modulo MK, So you're picking out one congruence class modulo each modulus. The Chinese remainder theorem tells you that you can satisfy, or you can find integers x which satisfy all of those congruences. You can find an infinite number of integers which will satisfy all of these, but they all come from the same congruence class modulo the product. So when you multiply all the moduli together, you get some big number, right, for multiplying all those together. And there'll be one unique congruence class modulo this big modulus, which simultaneously solves all of these congruences. So it simultaneously is congruent to B1 modulo M1, B2 modulo M2, and so on. So it provides a assurance that a set of simultaneous congruences, if you're looking at the solutions, a set of simultaneous solutions modulo different moduli that are pairwise coprime, it assures you that they can always be satisfied simultaneously. And satisfied simultaneously uniquely modulo the product of all of them. Now, the way it's stated there, it just looks like an existence proof. It just says that there is, this thing does have a unique solution. But the method of proof actually provides you a method of constructing the solution, finding the solution. I won't work through it line by line. We don't necessarily have enough time to do that, but I'll just pick out the main points. So the CRT, Chinese remainder theorem, cathode ray tube, Chinese remainder theorem. So the main points of the proof. Well, it really works by constructing the solution. And that's what we'll look at now. There's some small little technical, tying up of loose ends to prove that there's only one unique solution. But the main kind of thrust of it, the main kind of idea, is providing the formula for the solution. So we need some ingredients. So first of all, capital M is the product of all the little moduli. Easy enough. Capital M I with the subscript I is equal to that large product, but you cancel out the ith little modulus. So capital Mi is the product of all of the moduli except Mi. Yeah? Product of all of the other ones. Now, what we need to do is we need to make an observation here. Greatest common divisor of capital Mi and little mi is equal to 1. Okay? Because remember, part of the assumptions in the statement of the theorem is that each of these little moduli are coprimed. Mi is the product of all of them except for mi. So when you compare little mi to the product of all of the other ones, which is capital Mi, there's no common factors between those, okay? Because little mi is coprime to each of the other ones individually. So it's certainly coprime to the product of them all, okay? So then we let capital Mi prime congruent to, well, this is really the inverse of capital Mi modulo little mi. So these things are the ingredients, the Mi and the capital Mi prime. And then you see over the page, on page 46, then you see a big summation formula which provides the solution. BI, so the BI, remember, are in the original set of simultaneous congruences that you're trying to solve. Remember, it's x congruent to BI modulo little mi. So it's BI times the Mi times the Mi prime, and you're summing all of these from I equals 1 to 6. In other words, if you expand that sum, it's x equal to B1, M1, M1 prime, plus B2, M2, M2 prime, etc., etc. And the last one is BK, MK, MK prime. Okay, so this is a big, well, some number, just a load of integers multiplied together and added. So x is certainly an integer. And then what you do is consider this x modulo mi. Think about this big, long, complicated-looking sum. What is it congruent to modulo one of the original little moduli m1? Mi. Okay. Well, let's take the first one, for instance. So let's consider this modulo little m1. Okay, you see it's a load of things added together. So to work out what the congruence class of this x is modulo little m1, you want to work out what the congruence class of this is, the congruence class of this. You work out the congruence class of each of the terms, then you add them all together. However, when you look at most of these terms have a factor of m1 in them. Okay, because inside m2 is the factor m1. Okay, because what is capital M2? Capital M2 is the product of all of the little m's except for m2. So inside there is a factor little m1. So that means this whole term is congruent to 0 modulo little m1. So is the third term here, because the third term has a capital M3. And inside capital M3 is the factor m1. So the third term is congruent to 0. So all of these are congruent to 0 modulo little m1, apart from this first one. Okay, because there isn't a factor of little m1 inside capital M1. Okay, so this is non-zero, potentially. But then you look at this product. What is m1 times capital M1 prime? Well, remember, M1 Mi prime is the inverse of Mi modulo the little mi. So if we're considering this modulo little m1, these two are inverses of each other. So it just comes to 1. So these are all 0. These two multiply together to give 1 modulo little m1. So you're just left with B1, which is what you wanted, because you wanted your solution x to be congruent to B1 modulo m1. And then it works exactly the same for all the other little mi's. Okay? In general, when you consider this large sum modulo little mi, all of the terms are congruent to 0 except for 1, except for the ith term along the sum. Okay? Because all of them inside this capital Mj, inside there will be a factor of little mi, except for the one which has capital Mi in it. There isn't a little mi. But then you've got capital Mi multiplied by capital Mi prime, which is its inverse, so they cancel. So the only thing you're left with is the Bi, which is sitting there at the front factor. So this formula, if you like, constructs a solution. So we find that x is congruent to Bi modulo little mi due to properties, due to the divisibility
You can't see it.
Sorry, due to the divisibility and inverse properties of capital MI, capital MI. So everything else falls away, and X is just congruent to BI modulo little m. So that's certainly a solution. And then a few minor details show that it's a unique solution. The solution has to look like that. If you consider any other solution will be congruent to this X modulo the capital M product of all. So this is a solution. And the remaining details of the proof show that it is unique modulo capital N, which is the product of all the little mi. Okay. Okay, so in our tutorial this week, as well as ironing out any remaining difficulties with the linear congruences, we'll also have a go at some of the exercises there on the Chinese remainder theorem as well at the end of the chapter. So that'll be on Friday, won't it be? Yeah, tutorials then. So I'll see you then. Okay.